Hello, Calc. We're looking at this on Tuesday after class, so that's 10/4/16. And the topic for today is rate of change. So far, when we've used the derivatives, we have emphasized that they are slopes of a curve at a given point. And it turns out that sometimes it is useful and expedient to not only be thought of as a slope, but to be thought of as a rate of change. So we're going to go to the rate of change camp today and see how a derivative can help us. We're just going to get our little toe in the water, and we'll come back to this topic more and more. And you'll see how it simplifies some of the things that we've been talking about in physics, at least here at the school. So let's look at this example. So in physics, Emma, I think this has probably been in your experience as well. We learned that velocity is a displacement or a change in x divided by a change in time. So you see that we do have a rate of change going on here. So according to our statement here, the derivative can apply. For example, let's look at a statement. We often use s for position. When we're talking about f of x, you have a function with an x in it. Well, this is a position function where the independent variable within the function is time. So s of t is often used instead of f of x, where t is time. So s is position. And in this example, it's going to be in feet, and time is going to be in seconds. And say the equation for my first example, the position function is given as s of t equals negative 16t plus 100. Now in our class, we saw the position versus time in the form of a graph more than an equation. But any graph has an equation, so in class here, we're going to look at it like this. So you don't have to have the function in front of you, but this is an easy one to take a picture of. So it's going to cross the y-axis up here at 100 and have a very steep negative slope. So that is a straight line function. It is linear. And it's easy for us to see that the slope everywhere on that curve is the same. Now let's verify that with the calculus. So what I'm going to do is recognize that the slope of a position versus time graph is velocity. So slope in our class is the derivative. So I'm going to take the derivative of time. That is going to be I'm going to take the derivative of position with respect to time, and that's going to be velocity. So what is the derivative of this expression? Well, using the power rule, we know the derivative of negative 16t is going to be negative 16, because t is written with an exponent unwritten 1. So the 1 runs down in front and combines by multiplication with the negative 16. And then reduces the exponent by 1, which gives us t to the 0. Anything to the 0 is 1. So the derivative of the first term and the derivative of any constant is 0. So we have taken the derivative and we found that it is a constant value, negative 16, which we suspected from the graph. All right, so let's take a more interesting value for our graph, an expression for our graph. Let's say that we have an expression that is quadratic. So I'm going to take a new example here and say the position is given by negative 16t squared plus 16t plus 33. So again, this is a position equation. So I can find where this object is at any time by plugging in values for time. So if I'm thinking, where is this object at time equals 0? Well, I put in 0 for t and I get, oh, I left my t out for this middle term. So what do I get when I put in a 0 for t? I get this 0, 0, I get 33. So at the beginning of this problem, the object at time 0 is situated at 33. Then at time equals 1, we put a 1 here and a 1 here, and we see that its position is still at 33 because this becomes negative 16 plus 16 is 33. So then I'm not sure, I don't have my calculator here, but I could put a 2 in or 1.5 seconds. I can at any time, I can find the position with this equation. So now I'm interested in finding the velocity. So in physics class, we would graph this, and it's quadratic, so we would have a parabola of some kind, and we would find the slope at the given time of interest. So we would draw a tangent at that point and do a rise over run triangle to find the slope of the tangent. All right, in physics, that is well and good, but since we have the skills to take the derivative, which is another way to find slope, we're going to do that. So we're going to take the slope of the position curve, which is velocity, and we're going to take the derivative of that. The 2 runs down in front and reduces by 1, 16t becomes 16, 33 becomes 0. So here is the velocity function. So let's say that this is a diver. So they're starting on the platform that is 33 feet up, and it's going to go something like that into the water. And we have we could trace its position with this function. And now we have a picture of its velocity at any point. Look how easy it was to get from here to here, Joel. Did you notice? So anyway, so it's so easy to get from here to here. And we now have another function, because the derivative is in the second function. And this one tells me the rate of change of this one. Since this one is position, we have velocity on this one. So let's say, if we can use these two equations, when will he, she, whichever, when will he, she hit the water? And when will he, she, I'm not saying when this time, what is the velocity then? At what velocity? And at what velocity? All right, to answer that question, let's start with when will she hit the water? So what is the position, if we're started at 33, what's the position right when they enter the water? The position is 0. So I'm going to take the position function and put a 0 in there and solve that. If you would, without me, go ahead and factor out a negative 16, and what remains will be factorable. And there'll be a negative answer and a positive answer when you solve that by factoring. And if you can prove to yourself that the time turned out to be 2 seconds. So the other answer was -1, but negative time, we're going to reject that answer and go with the positive one. So verify that the answer to this is t equals 2. And now let's come down here and answer at what velocity is that happening. At that time, what is the velocity? So now that we're asked for velocity, we're going to use this equation. So we have velocity equals -32t plus 16. But we want to know at time 2. So we're going to substitute 2 into the time for time in the velocity equation. And I usually indicate with a line that I'm going to substitute 2 into that equation. And that came out to be negative 32 times 2 plus 16, which is negative 48. And that was feet per second. All right. Like I said, we're only going to put our toe in the water. This person is entering the water, but we are just putting our little toe in. All right, so if you would then take this information with you to class, and we will use it one day. All right, I'm kind of treading water. I'm not covering a lot each evening because we want to practice derivatives. We haven't had them for very long. So you'll see our class time is constantly doing that. And we're also one other lesson behind in our practice, the alternative way to calculate derivatives with a limit. And we did one other thing that night. It escapes me now, but oh yes, so we did talk about this a little bit, about differentiability and continuity, how those work together on a graph and in an equation. All right, so treading water, going a little slower so our classwork can get where it needs to be. So with that, good night.